Here we are with another installment in our series on the basic analysis of rational functions. And as we move into the examples involving algebraic forms of rational functions, this information you can see on the screen here in front of you becomes more and more prominent. And so if I forgot to mention before, would this be something you'd want to have on your sheet of notes when you're writing an exam? I would say absolutely. This is something that a lot of people commonly get confused about, and very often they don't do enough examples to really get comfortable with it. And so if you're uncomfortable with it, that's probably a signal to you that you may want to do some additional examples. But anyway, let's look back at where we were. The instructions for all of these examples that we're going to be running through are the same. We're asking for the intercepts, both x and y, if they have it, vertical and horizontal asymptotes, and domain and range using interval notation. And it's easy to lose sight of the forest because you're looking at the trees. And so if you step back and look at the forest a little bit here, you'll notice that these examples we've chosen are fairly rich. They have a lot of things that are important to know. And so that's why I picked them. So the first one that we're looking at here, which we did in the last video, that one has the numerator degree of 2 and the denominator degree of 3. And so as you can read here at item number 2, because of that relationship between the degrees, it has a horizontal asymptote at y equals 0, otherwise known as the x-axis. And each of the examples that we're looking at is going to permit us to look at a particular facet of that numerator-denominator degree relationship. So here, for example, you notice that the numerator and denominator have the same degree. And then the next example, the numerator has a larger degree. And then the last example, the numerator and denominator have different degrees. The denominator is larger, as in the first example that we did. So we're giving you an opportunity here with all of these to kind of look at examples that have a lot to offer. And we're trying to make everything as clear as possible. So let us take a look at this next one here. Same instructions as before. We want the intercepts, we want any asymptotes that may be there, and we would also like the domain and the range. Now hopefully you would notice, as with the first example, that this is not factored either in the numerator or denominator. And so that's really the first order of business. If you're going to try to analyze this, you're going to have to get some factors. And we're assuming, again, that when you come into our course that you have that factoring stuff down. If you're struggling with the factoring, it may be a sign that you need to do a little bit of review of that. Anyway, in the numerator here, I need a couple of factors. It looks like I want to multiply to make 5 and add to make 6. And so by inspection, it seems to me that these are correct here. You should always check those factors to make sure they are. If you make a mistake at this factoring stage right here, the ripple effect is significant. It pretty much turns into game over, thanks for playing at that point, because it's going to go so far wrong that you just can't recover. Very important to make sure your factors are on the money. Now the denominator, I need factors of 2 and I need factors of 5, and I need to add to make 7. And so I'm thinking that this might do it. Whoops. If you check those factors there, it's hard to walk and talk and chew gum at the same time. If you check those factors, I do believe they're on the money. 2x and 5x definitely adds to make 7x. So we're good. Now you might notice something. You notice that you have a common factor of x plus 1. And so your first inclination might be to cancel that. And I totally agree. I would cancel it too. And so the end result after simplification would be x plus 5 over 2x plus 5. And that cannot be further simplified. Now you might be thinking to yourself, well, that's great. It's really a simple one. Answering those questions about intercepts and all that should be really easy, shouldn't it? And actually having that common factor of x plus 1 complicates things a little bit. It makes it a little bit harder to understand what's going on. So first of all, you have to understand that you can't do this cancellation well, let's say it positively instead of negatively. You can't do the cancellation if it's not well defined. And being well defined in this case means that the value of x equals -1 is off the table, both as an intercept, because you might be looking at that and thinking to yourself, well, hey, before the cancellation wasn't like x equals -1, wouldn't that be like an intercept? Because that's where the numerator is 0, right? And that's where your x-intercepts come from, is when the numerator is 0. And actually, it's not an intercept. It's going to have a hole in the graph at that value, because necessarily, let's back up and explain why. So when we say that the cancellation implies that it must be well defined, that is a fancy way of saying that x cannot be -1. And the reason that x can't be -1 is because if it was, you would have a rational expression of the form 0 divided by 0. And that is undefined. And so we cannot have x being -1, and that is clear from the get-go. And in fact, when you make that cancellation, you are tacitly assuming that x is not equal to -1. And so even though it may appear that there's no earthly reason why -1 would be excluded from the domain, which you're going to see in a couple minutes, it is, because you can't do the cancellation if that's in. So you got to remember where you started when you're looking at the final form, the x plus 5 over 2x plus 5. So anyway, let's answer the questions that they were asking us here. They first asked about the intercepts. And the x-intercepts are easy. Those come up again where the numerator is 0. And so you can see by inspection that you're going to have an x-intercept at -5, because that's the value that makes the numerator equal to 0. And if they're pressing you on a value or an ordered pair format for that, never know what your learning management system is going to want, then it would be -5, 0. As far as a y-intercept is concerned, that's going to be at f of 0. And so you can see in this case that if you put in 0 to the form of it, 0 plus 5 divided by 2 times 0 plus 5, it's going to be 5 over 5, which is going to be 1. So as an ordered pair, that's going to be 0, 1. Right. Next thing they ask about is the asymptotes. I don't know why I labeled that Roman numeral 2. That's kind of dumb. Don't judge too harshly. You'll be middle-aged one of these days as well, and you'll find that, there's a lot of issues associated with that. Anyway, asymptotes. Well, there's no slant asymptote, because you can only have a slant asymptote when the degree of the numerator is larger than the degree of the denominator. So that's not a concern here. We're going to have a horizontal asymptote, and as we indicated back on our PowerPoint slide, we were saying that when the degree of the numerator and the degree of the denominator are the same, you're going to have a horizontal asymptote, and it's going to be at the ratio of the leading coefficients. And so in this case, you can see plainly that the leading coefficient from the numerator is 1. And we normally don't write it, but just for clarity, we can say here that you have a 1 right there. That's the leading coefficient. It's understood, right? And the leading coefficient from the denominator is going to be 2. And so I know I normally do these in a certain order. Let me just go with what I'm talking about here. So horizontal asymptote, that's going to be at y is 1/2. And why is that? That's because the degree of, and you can reference whatever version of the numerator you want, the original one or the simplified one, it doesn't matter. But I'm just going to say it here, the degree of the numerator is equal to the degree of the denominator. And I'm abbreviating a little bit there just to make it fit on the screen. Now, as far as the vertical asymptote, well, those come from denominator zeros. And even though we might look back and say, well, didn't we have a denominator 0 at -1? Well, that's kind of a special thing. It's not going to give us a vertical asymptote, as you'll see. We'll graph it for you and we'll show you. But it will give a hole in the domain. Now, as far as the vertical asymptote, the only 0 here would be from 2x plus 5 is 0. And so if you isolate x, that's going to be -5/2, right? Or -2.5 if you prefer. So it only has the 1. And as far as the rest of this, when they ask about the domain and the range, hopefully the last video sort of emphasized this, but it never hurts to repeat. People tend to excel at ignoring the obvious. So the domain is very easily read from the algebraic form. The range, not so much. So domain and range here. Now, we were saying that because that cancellation that we did at the very beginning, that -1 is excluded from the domain. And it is. Even the calculator knows that. You'll see when we graph it. But anyway, we also have to exclude the vertical asymptote, right? Because that's a 0 in the denominator and division by 0 is undefined. So our domain is going to be as follows. You're going to have -infinity to -5/2, round parenthesis, union -5/2 to -1, and then -1 to positive infinity. Now the range, that one is tricky. You almost have to have the graph if you want to have an easy time of talking about the range. And so let's graph it. We'll show you what we're talking about here. Now, just to showcase that these two functions are, well, let's put it in as it originally was given. I think that's probably the most useful depiction here. So the numerator was x squared plus 6x plus 5. So we'll put that in. And those have to be encased in parentheses or the calculator is not going to digest it correctly. And then the denominator was 2x squared plus 7x plus 5. All right. And I would probably start with a standard zoom just to, sorry. I'll just go zoom 6. So there's my graph. And it may not be evident at first glance that there is a hole at -1, but there is, because watch. If you put in -1, you notice how the y value is blank. And so that's the calculator's way of telling you that the function is not defined at -1. So even the calculator can recognize this fact. Now, in terms of the other features that we talked about, we're really here for the range. But you could verify a couple of the other features if you wanted to. For example, if you put in -2.5, which we said was an x-intercept. Sorry. I was kind of hoping it would give that to me. Oh, that's a vertical asymptote. Sorry. Got confused again. -5 is an x-intercept. I was going to say that something looks wrong on that graph there because it's not crossing at that value. Yeah, the asymptote is -2.5, as the calculator is indicating, right? Even the calculator knows that there's an asymptote there. It usually doesn't shade them, though. So put in -5. There you go. You can see that's an x-intercept. Now, we were talking about the range, and that is the trickiest thing about this here. You'll notice that the graph definitely has a horizontal asymptote, but where that is a difficult question unless you've already done the analysis. So we already we already explained that, well, there's a horizontal asymptote at 1/2. And I don't know that it's going to be helpful to graph that as a separate line on here. I guess if you insisted, we could. It's not that big of a deal. You're just putting in 0.5 and then graphing that. And so you can see that, yeah, definitely it would appear that there is a horizontal asymptote there. What's not good about this view, though, is that it might look superficially like the graph comes in contact with the horizontal asymptote. It does not, in fact, come in contact with it. And so that is a hole in the range. You will not be able to find an input value for this function which will spit out y equals 1/2 as an output value. And if you don't believe me, you can zoom in on this and see how the function behaves as you go out to large values of x on the negative side or large values of x on the positive side. Now you kind of have to open up the window a little bit to see that, but you can use the trace function here like this. Watch the y values. Okay, you can see that we're right there at the intercept, and so it's spitting out 0, 1 like we said it would. But as you move to the right, look at how the y values are behaving. They're getting smaller and smaller, but they're not going to 0. They're going to 1/2. And in fact, if you don't believe me, you can open up the window and see. Do it like this. Let's open it up so we don't have to move around so much. Let's go negative 100 to 100, and we'll make the scale 10. And then on the y side, we don't really need that much y, so let's go like negative 5 to 5. Scale of 1 is fine. So here's our graph. Now, of course, it's not an optimal view, but for what we're using right now, it's a good view. So again, I'm going to trace, and it's starting me at the y-intercept there, and I'm just going to keep going to the right. So look at the behavior of this function. I'm almost at 100 right there. I'm almost about to leave the window. And you can see that the x value is 95, but the y value is like 0.51. You can go as far to the right as you want, and the y value is never going to go below 0.5. Likewise, if you trace the other side of this, it's going to jump over the asymptote. There it is. So now I'm on the flip side, and you can see that the y values are going to be increasingly negative there. Notice the y value. It's going to increase towards 0.5, but it's never going to go above 0.5. And so no matter how much you widen up the window, you're never going to be able to get the y values to equal 0.5. It never contacts that that horizontal asymptote. So long story short, what we're saying here about the range is that the range goes from minus infinity to 1/2 with a round parenthesis, and then 1/2 to positive infinity. Now I don't have a picture of it here that I can shade on, but basically that hole in the range at 1/2 is because of the horizontal asymptote. The function does not cross it. Stay tuned for the next video.